Hey guys, welcome back. Now that we've initialized the model, it's time to train it. Before doing so, let's move on to the next cell and change the model statement from classifier to Lynette. There will be no need to pass anything into our initializer, and once we output the model itself, we can visually observe what was previously stated, such that the first convolutional layer has a depth of 20, the output in the second convolutional layer has a depth of 50, and 800 node parameters are inputted into the fully connected layer, and 500 node parameters will be in the hidden layer of the fully connected network, with 10 output nodes in the output layer denoting our 10 MNIST classes. Further confirmation that we've built our model correctly. To run the convolutions and train our model, we will be making use of Google Colab's free Tesla K80 GPU. We do this by going over to Runtime, change runtime type, and the hardware accelerator simply specify as GPU. Save, simply providing superior processing power. And now we can go ahead and train our convolutional neural network. There is a preliminary step, however, involving CUDA tensor types that implement the same function as CPU tensors, but they utilize GPUs for computation. This preliminary step will be taken into account by going on a cell right below the top one. We're going to press Alt-Enter, and it seems like we have to run the cell above it first. So what I'm going to do is fast forward this video until the installation is complete. I'll see you guys in a bit. Welcome back, guys. We start by specifying device is equal to torch.device CUDA 0, GPU 0, and we specify the following. If torch.CUDA.is available, else we simply resort back to CPU. Alright, and now we first start by assigning our model to our device. So we'll go back to Lynette, and we write Lynette.toDevice. And now whatever tensor types that are being passed into our model, we assign them to device as well. So for instance, in our training cell, before passing in our images and labels to compute the loss, what we'll do is actually set inputs is equal to inputs.toDevice, and we also set labels is equal to labels.toDevice as well. And one more thing that's important to point out is that since we are dealing with convolutional layers to which the inputs are first being passed into, we will pass in the full dimensionality of these images. There is no need to flatten them. Thus, we can remove this line of code and this line of code as well. We do not need them. You would have needed them had you been dealing with a regular feed-forward neural network, but in this case, the full 28 by 28 image is being passed in for the kernel to be convolved and extract the appropriate features. So make sure to remove those. And aside from that, everything should remain the same. It looks good. Okay, and doing the same thing for the val inputs, we will set val inputs is equal to val inputs.toDevice. Again, this is just a preliminary step to get up and running in order to properly train our model using GPU. Val labels is equal to val labels.toDevice. Alright, and there's only one more place to do this. We do the same thing, and that's in our last cell where we're making predictions on the following images and labels. What we're going to do is we're going to set images is equal to images.toDevice, labels is equal to labels.toDevice as well. Alright, as we are now working with CUDA tensor types and training on GPU, we now run the training process and evaluate the loss and accuracy of our new model. We will also test the effectiveness of this model in a variety of images. Runtime, run all, Welcome back, guys. Starting the training process, we can already see that the network starts off performing better. The starting validation accuracy is 97%, much higher than our initial validation accuracy with the simple deep neural network. I recall it was about 70% before. The loss is also significantly lower, at only 0.0954. The accuracy values only seem to be converging to high values as the training process proceeds, while the loss continuously goes down as well. This is really nice to see, and shows the effectiveness of convolutional layers within the network. Skipping ahead in the training process, we can see that the model converges to a final training and validation accuracy of about 99%. This is much higher than the accuracies we obtained earlier. However, we can see that the training accuracy by the end of the training process is higher than the validation accuracy. While the difference between the two is not too large, this shows signs of overfitting in our network, which can also be visualized in the following plots. Clearly, some signs of overfitting once you get to epoch 7. This can be solved using a simple dropout layer within our neural network. So as effective as this convolutional layer was, we are going to introduce another quick technique to reduce overfitting of our data. We are going to go back to our Linnet class, and we're going to add a specific layer type that will help reduce overfitting of our data. This layer type is called the dropout layer. This layer essentially functions by randomly setting a fraction rate of input units to 0 at each update during training, which helps prevent overfitting. The process can be seen within this image. The image shows a standard neural network, and it shows the same network after dropout is applied. You can see that some nodes have been turned off and are no longer communicating information along the network. As mentioned earlier, the dropout function randomly selects a predefined fraction of nodes to be turned off. What this means is that every time the network updates parameters during the training process, it selects random nodes that it is going to turn off. So while our figure shows specific nodes that have been turned off, it's important to note that a different set of nodes are turned off with each update. This process works to prevent overfitting because it forces the neural network to use various combinations of nodes to classify the same data. As with each update, a random set of nodes survive the dropout process. Each node is forced to learn the data set in a more independent way, with a unique neural arrangement each time. This causes the neural network in general to become more versatile and allows the weights to be more uniformly distributed along the network. Now, when this network is used on new data, dropout is not used, and all the neural nodes are used to classify the new data. When dropout is no longer used, the nodes can combine all their independent learning to form a more effective neural network. This results in a network that has reduced generalized error and demonstrates less overfitting when it is exposed to new data. A good, albeit simplified, example of this phenomenon is to imagine the following situation. Imagine a simple perceptron model with 2 input nodes and 1 output node. Our system is relatively simple, and it functions by having neuron 1 and 2 feed data into neuron 3, and neuron 3 combines this data to give an output. Now let's assume our network functions as follows. Neuron 1 has been well trained and feeds the correct input to neuron 3 about 90% of the time, while neuron 2 does not perform as well and seems to provide accurate input to neuron 3 at random. Therefore, as the network receives more training, it simply learns to listen fully to neuron 1 and completely ignores the input associated with neuron number 2. We essentially get a perceptron that behaves as follows. This can be viewed as redundant because 2 neurons are essentially just behaving as 1, and neuron 2 becomes obsolete. This is where dropout plays a key role in improving the effectiveness of the network. Applying dropout to this network means that at random instances, either neuron 1 or neuron 2 is turned off. When neuron 2 is turned off, not much changes as the network was ignoring this neuron anyways. However, in the cases when neuron 1 is turned off, the neural network is forced to listen to neuron 2. While at the beginning, this might seem like a bad situation, due to the poor performance of neuron 2, it is actually a good thing. This is because these situations force the second neuron to learn and adapt to the data as well, independently of neuron 1. This also forces the neural network to listen to neuron 2 and provides resources towards improving the accuracy of neuron 2. Now, when the network moves on to testing data, neuron 1 and neuron 2 start to work together more efficiently. While neuron 1 is still correct 90% of the time, neuron 2 has also been trained and provides an added level of accuracy that pushes the accuracy of our network over 90%. This is just a simple example of how overfitting can provide uniform weight distribution over the network and can decrease generalization error. In more complex networks, this results in decreased overfitting. Now that we've grasped a better understanding of the dropout layer, let's try implementing it in code using PyTorch. Now we access our model that we had created earlier, and we place the dropout layer within our neural network. However, more than one dropout layer can be used in a given network to obtain the desired performance. The location of these layers in the network can also vary. You can place them between the convolutional layers or between your fully connected layers. Typically, the dropout layer is used in between layers that have a high number of parameters, because these high parameter layers are more likely to overfit and memorize the training data. For this reason, we will attempt to place our dropout layer between our two fully connected layers to fix our overfitting problem. So going to our init function, we will name this layer dropout1 and linking it to self. And this can be set to equal to the PyTorch_nn.dropout module. Like so. The only argument we need inside this module is the dropout rate, the probability of a given node being dropped out. We will use 0.5, as this is the recommended rate provided by the researchers that first proposed the dropout technique to reduce overfitting. And the next step of this process is to go to our forward function and refer to our defined dropout layer. As we want to place it between our two fully connected layers, we add a space in between them, and we can refer to the dropout layer by simply writing its name, dropout1, attaching it to self, and we also feed the value x as input into this layer. Finally, we finish by storing this new value into another x variable, and that concludes the addition of the dropout layer. Let's move forward and put it to the test. Recreating our model, and I will see you guys on the other side. Alright guys, welcome back. We see that the network still has a relatively high accuracy, and the convergence is similar to before, as both the training and validation accuracies are converging close to 99%. You can see that as we progress to 13 epochs, the validation accuracy is slightly higher than that of the training accuracy, and they're not too different thereafter. This means that our overfitting issue has been dealt with, and our network has been trained effectively, with a validation accuracy reaching approximately 0.99 and 99%. Our model should predict most of our images correctly. The graph output also shows a very nice graph, with a loss converging very close to 0 and an accuracy converging very close to 100%. The validations and training accuracies are very near the same value, with minimal signs of overfitting. This is indicative of an effective training process. And now, running all the cells below this one, we can test our model. And we get an error such that the dimensions being passed into our model are not compatible with what should be passed in. First things first, we do not need to flatten our images anymore into 784 rows of pixels. So we can go ahead and get rid of that. And recall we must make use of image.toDevice. By doing so, let's actually comment this out and print image at index 0. .size, giving us our dimensionality from earlier, and ultimately to ensure 4-dimensional input for 4-dimensional weight, what we're going to do is unsqueeze this twice, .unsqueeze 0 dot unsqueeze 0. And what this will return is a new tensor with a dimension of size 1 inserted at the specified position 0, and it does that twice. And that is how we will account for the extra dimensionality that's needed to satisfy the following error. Okay, and we set that equal to a new variable img. This will remain the same. Output is equal to model img. Pred is equal to torch.max, output 1. We simply print out the prediction. Given this error, let's recall this images. Call this image and reference images accordingly. Image, and we should be good to go. All right, and we see that the model accurately predicts the imported image representing a value of 5. This is really good. Let's try it out here as well. Once again, expected 4-dimensional input, but got 2-dimensional input of size 100 by 784. We start by removing the following and pass in the images as is. This should work just fine as we have a bunch of images, so this should account for that extra dimensionality. We should be good, although I am expecting an error, and the following can't convert CUDA tensor to NumPy. Use tensor.cpu to copy the tensor to host memory first. This error actually stems from the image convert function. You cannot convert a CUDA tensor to NumPy, and so where we are converting it, we must use tensor.cpu. We will do so right over here. Tensor.cpu.clone. Trying that again. All right. And we see that the model accurately predicts all of the test images, whereas our previous deep learning model was unable to predict the following image. Congratulations, you have effectively trained your very first convolutional neural network and have successfully classified the MNIST dataset. Moving on to the next section, we will look at techniques for classifying more complex datasets by introducing more complex deep learning architectures, and a useful technique referred to as transfer learning. I hope to see you there.